Welcome to our talk on conjecturing-based computational discovery of patterns in data. I'm David Edwards, and other speakers today will be Paul Brooks and Craig Larson. All three of us are from Virginia Commonwealth University, and our other collaborator is Nico van Klinkhout from Ghent University in Belgium. We are it's nice to have a team from such kind of a diverse background here. We've got Paul, who's from operations research. He's an optimization guy. I'm a statistician. Craig's a mathematician, and Nico is a computer scientist.
So previous work related to what we're talking about today, which is on automated pattern discovery and data, includes computational scientific discovery. Much of the early work was driven by discovering patterns in chemometric data. Langley has a recent survey, including a lot of his important work in that area. There's also been a stream of research in symbolic regression, which is using genetic programming to approximate a target function based on data. And the two of these have been kind of fused together recently for computational scientific discovery in recent work. Alongside that, the machine learning community, which has traditionally been about black box modeling and leveraging complex patterns without revealing them to the investigator, has more recently emphasized explainability and interpretability to support understanding. And the efforts in this area has been mostly about identifying important features, using rule-based modeling, or using sparse methods. There's also been some work in automated feature generation. Unlike what we're talking about here, where we're looking to enhance understanding, automated feature generation, the focus has been on improving prediction performance. There has been a little bit of work in statistical methods that are related, and that involves the random GLM method, which is involves randomly generating polynomials that and checking their fit to data.
So, as Paul said, our motivation really does go back to the previous focus that a lot of machine learning methods have had on just being black box models. If you look down here at the bottom, it's just kind of a standard look at a neural network. And a lot of these methods really do a great job at generating accurate predictions. But although they really do a nice job of leveraging the relationships that are among the features, they fail to expose the fundamental model to the user. And the purpose of what we're doing is to actually provide a mechanism for exposing the fundamental model, or at least being able to discover it.
So our first example is a bit of a confession. I collated a data set from Redfin, which is a residential real estate data, for a competition for my class. So I downloaded a number of features on these houses, and the task was to build a model to predict whether a listing would be above or below 300,000 based on a number of home features. And when I created this data set, I accidentally left both square footage and price per square footage in the data set. The feature names were masked a little bit, so it wasn't obvious that this was in there, but all the students needed to do in order to get over 99% prediction was to just multiply those two features and apply a threshold. Well, after about 4 or 5 weeks of applying different machine learning methods to this data set, some of them had achieved high accuracy ratings, but none of the students realized that all that was needed was this simple interaction term. So one of our motivations for this work is trying to discover such simple but nonlinear features in data that will enhance prediction efforts.
Another motivating example is this gravity example. We were looking at the possibility of recovering the dependence of a gravitational force on the mass of two objects, M1 and M2, and their distance, R. And so you can see off to the right there, the nonlinear relationship. And we created a fictional data set that used a predefined value for K that was chosen as a random number between 0 and 1. You can see the actual value that we used here in this fictional data set. up there at the top right, you can see a small, very small subset of the data that was generated, again, in the hopes of using this conjecturing framework to actually completely recover that dependence of F on those three variables. So we have two versions of the conjecturing algorithm that we're going to talk about. The first is an invariant version. And what that's going to be doing is producing bounds, both upper and lower bounds, on a numerical feature of interest. So as a first example here from the real estate data, it might generate a bound such as the year built being greater than or equal to HOA per month, that's homeowners association, times the log of 10 divided by the log of 2 times the days on the market. And so we're looking at creating a number of those types of bounds for the numerical features of interest. Then there's the property version, and that's going to produce conditional statements that are sufficient conditions for our target variable to evaluate, say, as true. A couple examples of that might be, let's say the property type, is it a multifamily home? If so, then it's going to evaluate to is above 300,000, or if the number of bathrooms is greater than or equal to negative 300,000 divided by price per square foot plus square footage would evaluate to is below 300,000.
So we use these two conjecturing frameworks to support both regression and classification modeling. So now I'm going to give a little bit more detail about how these, how the conjecturing process works. It's based, the invariant conjecturing process is based on deriving bounds. And so here we have a number of instances on the x-axis. In the previous example, you can think of it as houses. And then we have the value, the target value of interest. Okay, so for the first 6 instances or so, we have the actual value, and together they form a function. And so the conjecturing framework generates expressions of increasing complexity and applies them to the instances and checks to see if they're valid upper bounds for each of the instances. And if it is, for each of the instances we provided, then it's retained as a valid upper bound for the target value. If the conjecturing algorithm tries a function that works for some of the instances but is violated, it's not a valid upper bound for some instances, then we discard that relationship. We can have multiple upper bounds, some of which dominate on some instances and also on others, and we can retain those as well and see if they are interpretable or helpful. And then the minimum of those bounds is also a valid upper bound. We can do the same thing for lower bounds and then take the maximum of several lower bounds, and those form a valid lower bound on the target value. The idea being that perhaps these bounds will give the investigator ideas about what are valid bounds and what is the true target function. The property conjecturing version of conjecturing is to discriminate examples that are points that have the target property versus those that do not. So the ones that have the target property are in green, and those that do not are in red here. And so what we're trying to do is generate sufficient conditions to cover the space of the target property. So if the first condition, you see that it is a sufficient condition for a subset of the examples that satisfy the target property, but not satisfied by those that do not have the target property. So if we try another condition, this covers another subset of examples that have the target property, but is not true for those that do not. So it's a sufficient condition. The condition 3 is not valid because it evaluates to true for some instances that do not have the target property, so we discard condition 3. And we would look for a union of conditions that cover all the target properties. And the idea is that this union of conditions would be helpful as Boolean attributes in a classification effort.
In the next experiment, we took a classical database on letter recognition from 1991 that has 20,000 samples of computer-generated capital letters, 20 different fonts and variations of each of the letters. And what we wanted to do was generate sufficient condition conjectures for class membership. So to figure out something that would guarantee that a letter was a letter A or a letter B and so on. And what we did is took each one of these samples, comes with 16 numerical invariants. We first generated invariant relation conjectures for each of the letter types. They were true for each of the samples from this class. We got 435 invariant relations total. And these are, while they're true for each of the letters, they're Booleans in general. For any sample, they'll evaluate to true or false, and they can be used as inputs for the property relations conjectures. And we did that then for each of the 26 letters and got some really surprising and interesting results. While we weren't trying to get, we weren't going for accuracy, or that wasn't our primary goal. Data mining tools can do really great, much better than the original experimenters from 1991. We were interested in interpretable conjectures. So in one instance, for the sufficient conditions for a sample to be a letter F, we got the conjecture that X box is less than or equal to width. It's a little bit opaque, so let me tell you what the X box is. The X box is the measurement from the left edge of the sample to the leftmost pixel in the sample. So it's a measure of the white space on the left, and the width is the measure from the leftmost pixel to the rightmost pixel. And so this conjecture says if the white space is no more than the width of the letter, then the letter is an F. And that was actually true for 93% of the test letter Fs, and of the non-test letters, it was true for 7.4%. So it's a 7.4% false positive rate. And the interest here is that this X box is less than or equal to the width is something that can be investigated. Why? Why does that condition suggest Fness? So this is a contribution to the theory for letter classification. And that's what some of the letters from the sample looked like. Those were the Fs from the original Frey paper.
So ongoing work, we're looking for new ways to handle noise in recovering these relationships. Also working to discover constants of proportionality and bias terms.
Also interested in using conjecturing as a way of reducing model spaces, particularly with designed experiments. Anytime we're looking at building models where we have a huge model space but fewer data points, the model space can explode very quickly, and perhaps conjecturing would provide us a way with making the model space more manageable to do typical variable selection techniques.
Our code and the examples from the home, real estate, and gravity data sets are available on GitHub at this address.
Thanks for your interest. This presentation was brought to you by the letter F.